Welcome back to my channel. I hope everyone is doing great. My name is Ravi Teja. Let's solve 11th problem of dynamic programming study plan, minimum falling path sum. Okay. The problem statement states, given an n by n array of integers matrix, return the minimum sum of any falling path through the matrix. A falling path starts at any element in the first row and chooses the element in the next row that is either directly below or diagonally left or right. Specifically, the next element from position row column will be r plus 1 column minus 1 r plus 1 column r plus 1 column plus 1. Okay, if you are standing in this particular position, you can either go to the left or you can go to the downward direction or you can go in the right. Okay, so these are the three possible cells from which you can reach from this particular cell. Okay, now you have to identify, you can start from any one of these cells and you have to choose a particular path. Okay, if you see, if I start at this particular position, I can take down followed by down, or I can take down followed by right. So the sum for this particular path is 2 plus 7 plus 2, which will be 15. Sum for this particular path will be 16, and there will be various combination of these paths. Okay, I can go from 1 to 6 followed by 8, 1 to 4 followed by 8, 1 to 5 followed by 8, 1 to 5 followed by 7 or followed by 9, and so on and so forth. Okay, so there are so many possible paths which you can choose. Among all those possible paths, you have to return the minimum path sum. Okay, now let's say I'm standing at a particular index I comma j, and we have a function. Let's define a function f of I comma j, which will tell me the minimum sum of falling path from I comma j to the last row. Okay, the moment you reach the last row, that means I don't have to further process anything. I can straight away return the answer, right? So at any given position, I have three options: either to go to the left or to go to the right or to go to the down in the next row. So basically I have to go to the next row, and if I go choose the left cell, that means I plus 1 comma j minus 1, I plus 1 comma j, which is for right, I plus 1 comma j plus 1. Sorry for this, I am correcting it. Okay, so I plus 1 j plus 1. Okay, now I can basically choose from any of these options I have. So since we have to return the minimum path, we should basically take minimum of all these possibilities and sum the current cell value to this minimum value, and that will tell me the minimum sum of falling path from I comma j to the last row. Okay, now that I have defined my recurrence relation, we should also define the base cases, right? So the moment I have exceeded the last row, that means I have to return 0, or else if any one of my indices is exceeding, if it is going out of bounds, then I will be returning a max value, indicating that the sum is not possible at all. Okay, let me show you the bottom-up approach, top-down approach implementation first. Okay, so in the top-down approach, we'll just replicate the same recurrence relation which we have derived. So this is the recurrence relation which we have derived. So I have defined a function f which will take both I comma j as an input and tell me what is the minimum sum, falling sum, to reach the last row. The moment I have exceeded the last row, that means I will be returning 0, indicating that I have processed all the elements in my path. Okay, now there are three options. One option is to select the downward cell straight away. So I'll just define a remaining which will be the minimum of all three options I have. Okay, first option is to go straight away down. So f of I plus 1 comma j, the answer coming from this. If I can only take the left direction if I am within the bounds. Okay, I am just checking whether j minus 1 is within bounds or not. If it is within bounds, then only I am calculating the minimum of remaining kind f of I plus 1 comma j minus 1. And I also have option to take the rightward direction. So if the right position also, if it is within bounds, then only I will be calculating answer to it and getting the minimum value. So far remaining will contain the minimum of all options I have, right, for a particular index I comma j, and my final answer will be the current position cell value plus the remaining. Okay, since we have noticed that this particular cell is depending on this particular cell and this is also depending on this particular cell, if you draw the tree diagram, you will notice that there are certain problems which will be overlapping. Whenever we have overlapping sub problems, we don't have to recompute the answers again and again. We'll simply catch the result and get the value back from the cache. So what I will be doing is I've just defined a DPR of size n by n. Okay, I just defined a DPR of size n by n, and then I'm just populating, I'm just first checking if my answer to my current function, if it is calculated or not. If it is calculated, then I will be returning the answer, or else I will be computing the answer and storing in my answer. Okay, and my overall final answer will be, I can start from any of the position in the first row. So the answer will be minimum of all these options from the first row. So I will be iterating from j equal to 0 to n and getting the minimum of f of 0 comma j, where j is basically iterating from all the values from 0 to n. So and then my answer will contain the minimum falling sum. Okay, if you submit this problem, all the test cases will be passed and this will be pretty efficient solution in terms of time complexity and space complexity. So let's analyze the space complexity. So we have initialized a DPR of size n by n and we are populating all the values. So this is the extra space which we are using for our top down approach. So the overall space complexity will be order of n square, and we will also have the call stack which will be taking big of n. So we can say the upper bound as order of n square for the space complexity. And for the time complexity, we are computing all the states. I is taking values from 0 to n, j is taking values from 0 to n, and for each state we are we are calculating all the states of n by n. So the time complexity is also order of n square because we are populating the entire DP array, right? So the overall time complexity is also order of n square and space complexity is also order of n square. We can actually, this is top down approach. Let's also look at the bottom up approach. Okay, in the bottom up approach, what we will be doing is we will be populating the DP array in the downward direction. So first I will be filling the DP array of the last row, and then last but one row, and last but one, and so on and so forth. Okay, so when I am in the last row, my answer to the last row will be straight away the matrix value. If I am not in the last row, that means answer will be coming from either from the left or down or from the right positions in the next row. So that is what I am doing here. I am just taking, this is the down position, and if I am in within the bounds, then I will be taking the left bounds value, and if it is not, I will be returning a maximum value, and in the right position, if it is also within the bounds, I will be taking the value, or else I will be returning the maximum value. So in the end, this will basically give me the minimum of all three options I have at a given position, and I will be summing up with the matrix value. Okay, in the end I have to take the minimum of the first row, answers from the first row. So that is what I am doing over here. And then my answer will contain the minimum falling path for the given grade. Okay, even this approach will take a time complexity of order of n square because we have two for loops which are running from 0 to n, 0 to n, and the space complexity is basically order of n square because we have a DPR of size order of n square, right? We can still optimize our bottom up approach in terms of space complexity, because at any given point answer to the current row is only relying on the answer to the next row. That means we only need one extra, at any given point we only need the answer to the next rows, right? So I will be just defining a DP array of size 2 by n. Okay, we will be having 2 rows and n columns in my DP array, and whenever I am calculating the answer, okay, that I will be populating my DP array with modulo 2. Okay, rest entire algorithm will remain same, but when I am calculating answer to this row, when I'm calculating answer to this, I will be populating the answers for I modulo 2 position. Okay, rest entire algorithm is remain same. Here we have reduced the space complexity from order of n square to order of n, and time complexity will still remain same, which is order of n square. Okay, if you like the explanation, hit the like button and hit the subscribe button, and don't miss to share your valuable feedback in the comment section. I will be posting solution in multiple languages such as Java, JavaScript and Python. If you are coming from any other languages, you can feel free to check the solutions. Okay, I will be also pinning the solution in the comment section. That's all about this video. Thank you.